In section 5 of module 5, which is the last section, we're going to look at graphs of rational functions. So a rational function is a function of the form y equals and then a quotient of two polynomials. What that basically means is it's y equals and then you have a rational expression. So for example, you can have y equals x plus 2 over x. Or you can use something called function notation, which is f of x equals x plus 2 over x. The important thing here is that in a rational function, the denominator is always going to contain a variable. So when it comes to graphing a rational function, there are certain parts that we have to identify before we can graph it. And one of those parts is a vertical asymptote. So a vertical asymptote is a vertical line that the graph approaches but does not touch. So if you're looking at a graph of a rational function like we have here, we want to identify where it appears to have a vertical asymptote. So when you're doing that, you look to see where these ends are kind of approaching. And if I look, they are getting really, really close to this invisible line, which tells me it has a vertical asymptote, which we typically abbreviate VA, at an x value of 3. And it is important that you include x equals because it is a vertical line and vertical lines are always of the form x equals. So there is a way to determine where a rational function has a vertical asymptote algebraically without graphing it. So that's what I'm going to talk about next, is how to find where a equation has a vertical asymptote. You are more than welcome to verify this graphically with Desmos on your own. I'm not going to do so in the notes. So we have y equals x minus 2 over x minus 4. So in a rational function, you have a vertical asymptote whenever the denominator equals 0, because that's when it's undefined. So if you think back to when in section 1, when we were talking about values that are excluded from the domain, we found when the denominator equals 0. It works the same way here. Whenever the denominator equals 0, that's when you're going to have a vertical asymptote. So I find out when x minus 4 equals 0, and I'll add 4. So we'll have a vertical asymptote at x equals 4. For our second example, we have y equals 2x over x squared minus 25. So again, we care about the denominator only, which is x squared minus 25. So we want to find out when x squared minus 25 equals 0. So when I factor this is a difference of squares. So it factors as x plus 5, x minus 5. So I'll find when x plus 5 equals 0 and when x minus 5 equals 0. So we'll subtract 5 and we'll add 5. And we're going to have two vertical asymptotes in this case. So we have a vertical asymptote at x equals 5 and negative 5. You are allowed to have more than one vertical asymptote. You do not have to have just one. You are allowed to have more than one. And it does affect kind of what the graph looks like. If you graph this, you're actually going to see 3 graphs because the vertical asymptotes are going to break it up on each side. The next feature we have is something called a hole. And a hole is a single break in a graph. And the way we find a hole, so we find holes by finding any factors that cancel. So if I'm looking at the graph of a rational function, or just any function that may have a hole, the way it works is you have your graph and you have like a little break in it, and then it continues. And this break right here is called our hole. Unfortunately, you can't really see it in a graph on Desmos. They're not readily visible like a vertical asymptote is. So we really rely on algebra to identify any holes in a graph. So we're gonna figure out where a graph has a hole, if any, and then we'll also find any vertical asymptotes. So for our first example, we have y equals x minus 2 over x squared minus 4. So my first step is to go ahead and put my equation in factored form. So my numerator doesn't factor, but my denominator is going to factor as x plus 2, x minus 2. And I can see I have the factor x minus 2 that is going to cancel for my numerator and denominator, leaving me with 1 over x plus 2. So that tells me I have a hole where x minus 2 equals 0, since that's my factor that canceled. So we'll add 2, and we get that the x value is 2. But the hole is a point, so now I want to find the y value. And the way I find the y value is I plug in 2 into my simplified equation. So I'm going to have 1 over 2 plus 2, which becomes 1/4. So I have a hole at the point 2, 1/4. For my vertical asymptote, I look at the simplified equation, and I only care about what's in the denominator of the simplified equation, which is x plus 2. So I find out when x plus 2 equals 0, subtract 2, and we have a vertical asymptote at x equals -2. In our second example, we have f of x equals 2x squared minus 50. So the first thing I'm going to do is factor out my GCF of 2 in my numerator. So we get 2 times x squared minus 25 over x plus 5. Now x squared minus 25, I'm going to factor. So 2 times x plus 5 times x minus 5 all over x plus 5. And there is a factor that cancels, x plus 5. And it's going to leave us with just 2 times x minus 5. I don't have to put it as all over 1 since the only thing in my denominator canceled. So for my hole occurs when x plus 5 equals 0. So we'll subtract 5 and we get that x equals -5. To find my y value, I'm going to plug that in. So 2 times -5 minus 5, which becomes 2 times -10, which is -20. So we have a hole at -5, -20. And I actually don't have to check for a vertical asymptote here. I'm not going to have one. Because the only thing that is in my denominator canceled and was a hole, I don't have a vertical asymptote. The last thing we have to talk about are something called horizontal and slant asymptotes. So a rational function or a rational equation has either a horizontal asymptote or a slant asymptote. It does not have both. It only has one. So what it is a horizontal line or slanted line, since there are two different things, that the graph approaches as the absolute value of x gets very large. So there's a couple of different examples of this. So we'll start with the example of what a horizontal asymptote might look like. So we'll have a graph. Let's suppose it looks like this. So my horizontal asymptote is going to be this line right here, because I look at the ends and they kind of are approaching that line but never crossing it. For example of a slant asymptote, you could have something kind of like this. So there's this kind of invisible slanted line that it's not going to cross. So again, you can't really identify a slant asymptote from a graph in Desmos. You could potentially identify the horizontal asymptote from Desmos, like we do the vertical line for the vertical asymptote, but we'll also talk about how to do this algebraically, just because you can't do it with the graph for a slant asymptote. So there's 3 different types. There are 2 types of horizontal asymptotes, and there is 1 method for a slant asymptote. So we're going to start with our horizontal asymptotes, which we're going to abbreviate HA. So the first one is the horizontal asymptote y equals 0. And that happens when the degree of your denominator is greater than the degree of your numerator. So for example, if I have y equals x over x squared minus 1, the degree of my denominator is 2, and the degree of my numerator, even though I don't write it, is 1. And 2 is bigger than 1, so it would have a horizontal asymptote of y equals 0. The second type of horizontal asymptote is y equals a number. And that happens when the degree of your denominator is equal to the degree of your numerator. So for example, if I have y equals x squared minus 4 over x squared, 2x squared plus 3x minus 7. My degrees are both the same. They are both degree 2. So the way I find that horizontal asymptote is you divide the leading coefficients. So the leading coefficients are the numbers in front of, in this case, it would be my x squared terms, or whatever your degree is. So it would be y equals, and the number in front of x squared is 1, and the number in front of 2x squared is 2. So I get y equals 1/2. And then for our slant asymptote, which there's no really like abbreviation. There is one way. It's always going to be y equals ax plus b. So it is a linear equation. And the only way you can get that linear equation is by performing long division. And the way I know you have a slant asymptote is if the degree of your numerator is greater than the degree of your denominator. So for example, if I have y equals x plus 4 in the denominator, but my numerator is x squared plus 7x plus 10, just making it up. So in this case, the degree of my denominator, which isn't written, is 1, and the degree of my numerator is 2, and 2 is obviously bigger than 1. And the only way to find a slant asymptote is by doing long division. The nice thing is it's going to be fewer steps than when we did long division previously when we were dividing polynomials. So it isn't going to be as much work. It is going to be a little bit easier. Okay. So let's do some examples where we find the horizontal or slant asymptote. So my first example, y equals x over x squared plus 1. So the degree of the numerator is 1. The degree of the denominator is 2, which means the degree of my denominator is greater than the degree of my numerator, which means I have a horizontal asymptote at y equals 0. That's simple. Second example, y equals 2x minus 3 over x plus 3. The degree of the numerator is 1. The degree of the denominator is also 1, which means they're the same. So I divide my leading coefficients. So I'm going to have a horizontal asymptote at y equals 2 because the leading coefficient in my numerator is 1. The leading coefficient in my numerator is 2. And the leading coefficient in my denominator is 1, and 2 over 1 is 2. For our last example, we have y equals x squared minus 3x plus 1 all over x minus 4. So the degree of the numerator is 2, and the degree of the denominator is 1. So in this case, the degree of my numerator is bigger than the degree of my denominator, which means I have a slant asymptote, so I have to do long division. So I'm going to set up my long division just like we did with polynomials. X minus 4 is going to go on the outside. X squared minus 3x plus 1 goes underneath. So what do I have to multiply x by to get x squared? That's x. So now I take x and multiply it by the x minus 4. I get x squared minus 4x. We're going to subtract. And my x squareds are going to cancel. And then we have negative 3x minus negative 4x. So it's going to change to addition. Negative 3 plus 4 is 1. So I have x. Bring down the plus 1. Now what do I have to multiply x by to get x? 1. So here's the nice thing for slant asymptotes. Once you have an x term and a constant, you can stop. I don't have to keep doing long division. I don't care about the remainder. I don't care if there is one or isn't one. I'm going to go ahead and stop. So I have a slant asymptote at y equals x plus 1. So much simpler process to find the slant asymptote using long division than it was to just divide two polynomials. So for our last example, we are going to put this all together and we are going to graph a rational function by finding all of its asymptotes and holes. And then what you can do is once we have it graphed is you can check that with Desmos. So we have y equals x minus 7 over x squared minus 1. So the first thing I want to do is check to see if there are any holes. So I'm going to factor my denominator, and it factors as x plus 1 times x minus 1. And since no factors cancel, I'm going to go ahead and say that there is no hole. So now I'm going to find my vertical asymptotes. So there are now two things in my denominator for my vertical asymptotes. X plus 1 equals 0, where I'm going to subtract 1, and I get x equals 1. And x minus 1 equals 0, where I'm going to add 1, and we get x equals 1. Sorry, this should be negative 1. Now I want to figure out if I have a slant asymptote or a horizontal asymptote. And I want to go back to my original equation before I did any factoring. So that's x minus 7 over x squared minus 1. And the degree of my denominator is greater than the degree of my numerator, which means I have a horizontal asymptote, and it's specifically going to be at y equals 0. The next things I want to find are my y-intercept and my x-intercept or x-intercepts, which is not something we talked about in here, but we did talk about it with quadratics, and it works the exact same way. So to find my y-intercept, we are going to plug in 0 for x. And you can plug it into your original equation, or if it's simplified, your simplified equation, it doesn't matter which. So we're going to have y equals 0 minus 7 over 0 squared minus 1. So those are going to cancel, and I get negative 7 over negative 1, which is 7. So my y-intercept is going to be at 0, 7. For the x-intercept or x-intercepts, it's actually a lot easier than a quadratic. I don't have to do any type of factoring. What you do is you set the numerator equal to 0. And it does have to be after simplifying. So you want to make sure you use the simplified form to solve for the x-intercept. And since nothing canceled here, I'm going to solve for when x minus 7 equals 0. So we add 7, and we're going to get an x-intercept at 7, 0. Let's go ahead and graph these things so we can get a sketch of our graph. So I'm going to start with my vertical asymptotes, which are at -1 and +1. And my scale does go up by 1s here. So each line is 1. For my horizontal asymptote at y equals 0, that's just my x-axis. Okay. Now I'm going to start plotting points I know I have. My y-intercept 0, 7, and my x-intercept 7, 0. So when it comes to drawing this sketch of the graph, I'm now going to kind of use Desmos to finish getting my sketch. So when I put this in Desmos, I see that I have kind of a quadratic in between, and on either side of the line, I'm kind of going down. And that's the sketch of my rational function. So let me know if you have any questions about finding vertical asymptotes, holes, horizontal or slant asymptotes, and then also the y-intercept or the x-intercepts, and then using that to sketch a graph.